most of you who are doing computer science will know that there is a significant chunk of graph theory and graph algorithms you learn in your algorithms course or in your discrete math course, and that tells you, I mean, the reason is because of the applicability of graph as a model to talk about a number of problems in multiple different domains. Okay. So my session today is to, so what is a graph? Well, graph is just a collection of points and edges which constitute some pairs of these vertices. Okay. So you have these points which we call as V, usually denoted as vertices, and then you have some edges which are pairs of vertices. Okay. Now this pairs, if it's an ordered pair, then we talk about directed graph, otherwise it's an undirected graph, and we might draw pictorially points and lines, but it's just a pictorial representation, but otherwise graph is just a collection of these two sets. Okay. And it's easy to see, you would have seen that many network problem, road network, electrical networks, airline networks, social networks, whatever, many of these network related problems can be modeled as graphs, and you can use some nice graph theoretic properties to solve some of these problems. So my focus today is to actually tell you about 2 or 3 problems which don't necessarily look like a network problem, but you can still model it as a graph problem and use some nice graph theoretic properties to study them. Okay. So in particular, I have a handout here where I have listed down some more than 15 problems, and your task is to model them as a graph problem. You may not have the machinery to solve them, but at least what you are asked to do is to model them as, what are the points, what are the edges, and what is the graph question we are trying to address in this, in trying to model this problem. Okay. So I will pass this around. This could be your interesting exercise during coffee breaks, lunch breaks, and you can form groups and just try them. Okay. And my plan is to pick some 2 or 3 and I will address them today. Okay, so let me start with this two IPL related questions I had asked in my abstract. So let's start the first question, which is that when you look at the points table, okay, this is the simpler question. So you have matches played, won, lost, drawn, and net run rate, and you have this, okay, points which is a function of lost, won, and drawn. Okay. So let's assume for our lecture there are no ties. Okay, either you win or lose. Okay. So the question I asked is this, that if you look at this column, today for example, CSK has completed 16 games and everybody else has exactly completed 15 games. Right. So at any point of time, if you look at this table, at least I don't claim that I have looked at every day, but on the days I have never seen this column having the same number all the time. I mean, I have never seen a day where this column has the same number. I don't know whether anybody has seen this, except when you start out with everybody is 0, and when you complete, everybody would have finished 16, 16, 16, 16. But never I have seen in between that all of them have played the same number of matches. Now the question is why? Is it because they designed the tournament that way, or there is no way of designing a tournament such that all these numbers will be the same? Did anyone think about this? This was in the abstract, so I expected somebody would have thought about this question, or you can think about it now. Is the question clear? Right. So I am saying not even any day. So let's say in one day there are 2 matches happening, you take stock after the first match, or take stock after any number of matches have been played. Look at this column, number of matches played. Is it possible that on any day all these numbers are the same? Yes, no? Or what is the graph theoretic question I am asking? can't be. I mean, this is the easier of the two questions I'm going to. All the teams are in the same distance.
From the source, but at a particular time.
What is the distance here?
Number of edges from the source.
There is no source. What is the source?
That is the starting date of the.
There is nothing to do with starting distance, right? I could just run all the matches on the first day itself and.
Because the number of teams is odd.
What is the graph theoretic question? Tell me first, and then let's look at the answer. So, what is the graph theoretic question?
Any complete graph must have
What am I looking for? So, when I finish, so what is the model? What are the points here? What are the vertices? What are the edges? Vertices are team. Each vertex is a team, and an edge is a game played between the two. Okay, is that clear? That's a graph. Now, in this graph, what am I asking? At any point of time, is it possible that every vertex has same degree, right? So, it is not the distance, it is a degree. So, degree of a vertex is the number of edges incident on them, that is exactly the number of games played, right. So, my question is, eventually this graph will be a complete graph. In fact, two edges between every pair of points, because everybody is playing two games. So, eventually when you start out with what is the graph? When no matches have been played, what is the graph? Null graph, isolated vertices, no edges, and then you are adding edges one at a time. And my question is, at some point, is it possible that all vertices have the same degree? No? Why not?
If it does so, then it becomes a complete graph where we reach to the.
No, why complete graph? I just want the same degree. The degree could be even 1, degree could be 3, right. I just want all vertices to have the same degree. Okay, so you said something about odd. So, what is that?
that is matches are played between two teams.
Yeah.
So we must pair up in the matches. So one team will be left to play with any team which had played already.
Yeah.
So eventually there will be a team with more number of games, a single team.
So, you are saying it is never possible if there are odd number of vertices. Is that what it is? What is the first theorem in graph theory you all learned? The sum of the degrees of the vertices is twice the number of edges. In particular, it is even. Sum of the degree of the vertices is even. So, let's make note of that and see whether that gives you anything, right. So, is twice the number of edges. In particular, for this purpose, all I care is even. Okay. So, does that give you a clue to answer this question? How many teams are there? 9 teams are there. Okay, let us make note of that. So, there are 9 teams. So, if everybody has same number of matches, then what is the total degree? Let us say if they all have k matches played, and total degree is what? 9 times. Is it not possible? K is even, it is possible. At least you can't rule it out, but clearly you can rule out when k is odd. Okay, so that's the first part of the answer. That at no point of time you can have every team having played odd number of matches. Is that clear? Whatever way you organize your tournament, because what I am asking is a subgraph in this complete graph, or at any point of time I am just throwing edges between pairs of vertices, and I want every team to have played exactly the same number of matches. Now, if it's not possible, to have all teams played an odd number of matches. Okay, what about even? Of course, 0 is possible. When we started out with everybody was 0. When we finish, everybody would be 16. That is possible. But in between, are these the two even degrees possible, or is there can you design the tournament, can you design the matches in a way that at some point everybody has played exactly 2 matches? Is that possible? No?
You can take an example where there are 3 teams. Say
Yeah.
if one team has played 2 matches.
No, your choice to design the tournament. You tell who should play what. That is my question. Is there a design? Is there a way to design your matches in a way that at some point, not at every point, I can draw a line and say, oh, okay, at this point everybody has played 2 matches. So let us take 3 teams, right? Okay. Is that possible? Just tell me who should play whom, and then we want to just say at some point everybody has played exactly 2 matches.
Yes. You can't do that because according to pigeonhole principle, there are odd number of teams. There.
Okay, like 3 teams, let's say.
Like 3 teams. If A and B are playing now,
Okay, let's say A and B has played. Okay,
and the next session B and C will be playing, you have only 2 sessions.
you have a choice. There is no 2 sessions, nothing. Everybody has to play at least 2 games, exactly 2 games. That's our final goal, right? So you can just say, okay, today A plays with B, and then A plays with C, A plays with F. Your choice of how do you want to design the game. Except you have, I am going to come and say, give me a day or give me some point of time where everybody has played exactly 2 matches. So what about this? You know, A and B plays, B and C play, and then A and C play. How many matches everybody has played? So it's possible. Is it possible in general when there are 9 teams? Yes. What would be the design? A cycle, right? So if everybody, you play A and B, and then 1 and 2, 2 and 3, 3 and 4 is one example of a design where everybody has played exactly 2 matches at some point, right? What about 4? Why with the same? That's one example. Okay, fine. Everybody has to play 2 matches, so 1 match is fine. But some other 6. Okay, so I'll leave that as an exercise. Okay, think about it. Come up with the design. For your lunch break, coffee break, is there a design that achieves every even degree, for every even degree there exists a time when all teams are played exactly D matches each. Sorry? I have no idea what Harare construction is. Just do something simple. You can tell me during the break what Harare construction is. I mean, we had a very simple construction, so just build on that. It's not very hard. Okay, good. So here is example of a naive looking question on some tournament which can be modeled as a graph problem. And the first theorem you learn in the graph theory is the sum of the degrees is even, using which you can say that odd number is never possible, but even number, you can design this tournament in a way that at some point everybody has played exactly even number of matches for every even number. Okay, that's possible. Think about it. Okay, so let me now go to the next question which I was asking, which is the title of my talk. Can CSK win the tournament? Well, by now the answer to that is pretty close to obvious, I think. At least we know what outcomes are required. Punjab has to lose today and Bangalore has to lose tomorrow, I guess, right? Okay, but let's look at a scenario where little more complicated scenario, and in general I have a set of there is a league tournament that's going on, and every team has played certain number of matches and they've got won and they've got some points, and there are certain games left to be played. The question is, I have my favorite team. Does this team still survive or is it eliminated? Okay. How do we model this as a graph problem, and how do we come up with what should be the outcomes of the remaining games so that this team is not eliminated? Okay. So, let us look at some examples. Let us say you have and let us say the points are okay. So, these are the points so far, and games yet to be played is, let us say, all pairs except so there is one match between every pair left to be played except Chennai Delhi match, let us say. So, here is a situation where these are 4 teams. Imagine every other team has been eliminated, or this team has played against them and got sufficiently large number of points. The contention is only between these 4 teams, and this is the current set of points, and these are the matches left to be played. Now, so when I say win, I am only talking about this playoff, right? It can even tie with some other team. That's also fine. Is CSK eliminated? Is it or not? Let's just answer this for this example. Okay. Is the question clear? We have, these are the points currently, and the matches to be played are all pairs except all the 6 matches minus 1, 5 matches left, and the CSK still have a chance. Okay. What is the maximum CSK can get? 20. There is only one match between every pair left except CSK Delhi. 15 is what it can get, right, because it is going to play a match with KKR and Mumbai Indians, and if it wins both, it can get 15. My question is now, is it already eliminated? Assuming all the outcomes are favorable to CSK going forward, is there a chance, or is anybody else going to get 16 or more? Yes, eliminated. Okay, Manu says it's eliminated. You saying it's eliminated? Okay, just tell me why.
KKR has yet to play CSK. KKR has 3 more matches.
KKR has 3 more matches. Yes, yes.
Suppose if it wins with all the 3, it is going to get 17.
Yeah, but suppose it is not, right? Assume everything, all the matches are now favorable to CSK. We are trying to see whether there is any chance at all. Is there a sequence of outcomes of the remaining matches so that CSK still has? Choose Delhi, it has to play Mumbai and KKR. Yeah, okay. Suppose it loses both. It loses both.
Then they will win.
Then both these guys will win. Okay.
Or if it draws, also
No, there is no draw. Okay, win or lose. Okay. So, okay, his argument is, look at Delhi. It has to play with these 2 matches, and we don't want anybody to go 16 or above. Suppose it loses both the matches, then these 2 get 15-15, and then when they play against each other, one of them has to get 16. Okay. So, you can try all possible combinations here, that there is no way CSK, somebody is going to get more than 16. Okay. So, here is the following is an averaging argument to prove this. Okay. Look at this set. What is their score so far? The total score so far is 43. Okay. And 3 more matches among them. Which means some 3 more wins are there. somebody is going to win out of the 3. So, totally that makes it 46. So, what? So, one of them out of this 3, is going to get more than 15, because 46 by 3 is more than 15, right. So far their point so far is this, plus there are some 3 matches among them left. Somebody is going to, that win is going to be distributed to somebody. So totally among them they have 46 wins. So one of them must necessarily, even without assuming all the matches to CSK they lose, even among them, one of them is going to get more than 15. Okay. So CSK is eliminated. The question is this the only kind of a proof you can give, right? I am interested in an argument, proof, an algorithm for this question. That one question you can ask. So CSK is eliminated. So let me just put some symbols and formally define the problem. So what do we have here? We have some teams. Let's say T1, T2, some Tn, and the points they have got so far, let's call them W1, W2 up to W1, and then there is some games left, some okay. So this is the setup of the problem. We have some teams, each one has already played, and at some point of time we are looking at it, and they all got certain number of points, that's W1, W2, Wn, and the games left between pairs of teams, some Gij games are left between I and j. Okay. So you are given this input, this vector of n and plus this n choose 2. Some of this could be 0, some of there is probably no game left between a pair of points. Now one possible observation from here, or that's a question. Okay, I am interested in, let's say, T1, which is the CSK. So T1 is eliminated if summation Wi I equal to 2 to n plus summation Gxy xy is in 2 to n is greater than, okay, and let us say T1 can win, max T1 can win is m, yeah. So this is the general statement out of this. Okay. So what we observed is that if the remaining teams together, the total points they have won plus look at the number of games among them to be played, that total number is greater than m, where m is the maximum this guy can win, times n minus 1, then necessarily the way you distribute this m times n minus 1, at least one of them will get greater than m. So T1 is eliminated. Okay. This is one sufficient condition. The question is it necessary? Is this the only way you get T1 eliminated? Here is an example where this is not true. So let us see. And this is the points. Games yet to be played is suppose this is the scenario you have, you have 6 points, 7 points, 11 points, 12 points, and the games yet to be played, every pair needs to play 2 games each. Okay. So there are like 12 games left. Now I ask the same question, is CSK eliminated? Let us at least try this necessary condition and sufficient condition and see if that works. What is the sufficient condition? What is the maximum CSK can get? there are 2 matches between every pair left. 12. CSK can get, because it's going to play 3 matches, 3 into 2, 6 matches, and if it wins all, it can get 12. But if you do the average here, it's 11 plus 7, 18 plus 12, 30. And how many more matches left among them? 6. 36 by 3 is 12. Okay, so it still stands a chance. At least it can tie. Okay, you can't say it's eliminated if you use this averaging argument. Okay, but using some other argument, you can show that CSK is eliminated. Can somebody see that? So is this clear that if you just apply this, I am saying if this happens, we already observed that T1 is eliminated. I am saying in this scenario, this does not happen, because if you do this for all these teams, whatever they have won, plus whatever matches, 6 matches left, that is 36, and when you divide by 12, that's divide by 3, you get 12. So it is not strictly more. Okay, but what? Last 2. If you take the last 2 and apply this, so their score is 23 so far, and how many matches left? 2 more left between them, so that's 25. So at least one of them is going to get more than 12. Okay, so the averaging argument tells you that CSK eliminated. So again, the answer is yes. So let me modify this. There exists a subset S contained in 1 to n such that summation I in S Wi plus summation xy in S gxy is greater than m times cardinality of S. Okay. Now the next question is this sufficient? Okay. I mean, here are some situations where we see that it's your favorite team is eliminated. The next question is this sufficient? And it turns out it is. So we are going to prove this. Okay, so let me just. I mean, this is superseded by this. So now we are going to argue that your favorite team is eliminated if the maximum it can get is m, and if and only if there is some subset of the teams whose the points won so far plus the matches among them is strictly more than m times this, then your team is eliminated. That's so we're going to prove the converse. And the next question is, what about algorithmically finding? So if we want to convince you that yes, it's T1 is eliminated, so he found this subset because it was a very small example. But if I have an n element set, how will you find? There are too many subsets to figure out. Is there an efficient, fast way of finding this subset? Okay, and the answer is again yes. Algorithmically, we can find this set if it's eliminated, and also if it's not eliminated, then also you need something. What do you need? You need a sequence of outcomes of the remaining matches, so that this guy still remains higher than, or at least greater than or equal to whatever points others can win. Okay, so there are all these questions. The converse of this statement, and if T1 is eliminated, give me a set which would witness this. If T1 is not eliminated, give me a sequence of outcomes which will ensure that this T1 team stands a chance. And the beautiful graph theory which we are going to appeal to answer this question is this famous Max-Flow-Minkut theorem. Okay? And we are going to apply, model this problem as a flow problem, and show that max flow will give you the sequence of outcomes, and min-cut will give you the set S. Okay, so that's the plan for the rest of the lecture. Okay, so in other words, what is the goal we have? Well, there are these games yet to be played, GIJs. Okay, we want to so this M you can find easily. Okay, so you take your team and assume that it's going to win all the matches it's playing with. So that's your M. Now we want to distribute the remaining the outcome of the remaining games to the teams in a way that nobody gets strictly more than m. That is the goal, right. So, this is like you know, you can start thinking it like a flow. We want to distribute some numbers to various elements, so that you know there is some conservation, but at the same time nobody gets more than m. Okay, so the flow we are going to so for this flow problem we need a source and a sink. So, we will start with, you have a source and you have a sink, and you have vertices u x y whenever g x y is greater than 0. So, if you have a pair of teams between whom the number of matches yet to be played is non-zero, then I am going to have a vertex here, and that there is an edge from S to all these vertices, and this edge gets a capacity of g x y. This is the number of games. The source is going to supply this number of games to this vertex. Okay. So, you have vertices like this. Okay. So, that is one set of vertices, and then this game is going to, so I have a vertex 1 for each team. So, this game, out of this g x y matches, some of them is going to be 1 by x, some of them is going to be 1 by y, and so T will absorb that. Okay. Well, how many matches I am going to make x to win? What is the maximum I am going to allow x to win? Because my goal to say that T1 is not eliminated, I want to make sure that everybody else wins at most m games, right. So, in particular x has already win wx games. So, I am going to put a capacity of m minus wx here. Okay. So, I can put the same capacity here, but it turns out it is convenient to put an infinite capacity here. Okay. So, flow network is a graph which has a source, a sink, it is a directed graph, and every edge has a capacity. Okay. What is the maximum amount of flow you can push through that edge? That is a capacity, that is what I am drawing now. Okay. Now, that is how this, so we will have, you know, it could be g y, sorry, u x z maybe. So, then it goes to x, z. Okay. So, that is my graph, that is my flow network. There is a source, sink, edges, one vertex for every pair of vertices among which non-zero number of games is to be played, and there is a vertex for every team, and this is the capacity of the edges. Okay. So, now what can you say if there is, so what is the maximum flow possible? If you look at this, maximum flow possible from S to T is summation g x y, yeah, right. For I have included g x y which are zeros also, but that is okay, that just counts 0. So, this is the maximum flow possible. Okay. And I claim first observation, which is not very hard, is that let us call this as some g star. If there exists a flow of g star, then what? My T1 is not eliminated. Is this clear? Because what this is saying is, I can, g star is the total number of games left, right. I can come up with an outcome of the games left in a way that, right. So, there are g x y flow will go out of it, that is the number of games to be played between x and y. Some of the games are 1 by x, some of the games are 1 by y, and the maximum 1 by x, maximum 1 by y is m totally, including whatever they have won so far. And that is true for every game to be played. So, there is a way, so this outcome, you know, this flow tells me how many games X is going to win, how many games Y is going to win. So, if there is a flow of G star, then there is a way of coming up with the outcome of the remaining matches, so that nobody wins more than M games, because I have constructed this flow network in that fashion. Okay. So, people who do not know flow, well, I mean, you have a directed graph, source and a sink, and there is a capacity on the edges, and we are interested in maximum flow. What is a flow? It is a function on the edges. You have to tell me how much flow goes through every edge, satisfying two properties. What are the two properties? Capacity constraint, that flow going across an edge should be, bounded above by the capacity of the edge, and there is a conservation constraint, that there is whatever flow comes in should go out of every vertex. Okay, that is the informal definition, where you can, it's pretty good to keep that in mind. Now, so now is this clear? That I have constructed this flow. If there is a flow, then T1 is not eliminated, because in fact I can give you an outcome of the matches, so that nobody wins more than M games. Okay. Now, it turns out there are very nice algorithms, very efficient algorithms to compute the maximum flow. So, you can apply that algorithm and get this outcome of matches. Okay. Based on augmenting path, you can start with the zero flow and find some path in the residual network, augment the flow and keep doing it, and it tells you that you can find the maximum flow. Okay. If not, what do I want to show now? That to show this statement, that if you do not achieve the maximum flow, then I want to argue that there is some subset that satisfies this constraint. Okay. And that I am going to appeal to the Max Flow Minkowitz theorem. What is the Max Flow Minkowitz theorem? This is due to Ford Fulkerson, and also has been independently proved by several others, which tells you that in a flow network, the maximum flow is equal to capacity of the minimum cut. Okay, what is the cut? Okay, is a partition of the vertex set, well, minimum ST cut. ST cut V into S and S bar, such that S is in S and T is in S bar. Okay. Any such partition of the vertex set is a cut, and the capacity of the cut is, look at all edges that go from S to S bar and add the capacity of all these edges, and that is the capacity of the cut. Okay. So, if this is the flow network, let us just put some, draw some. So, these are the capacities and this is the flow network. Then I want to find the maximum flow possible, and a cut is simply some partition of the vertex set. I can say, oh, with S is, this is one S and the remaining is S bar, a partition of the vertex set, and you look at all edges that go from S to S bar. In this case, there are 3 edges, add the capacities, and that is the capacity of the cut. Okay. Now, it is not very hard to see that your flow cannot exceed a cut, okay, because the cut capacity tells you how much you can push through that cut. But what is also nice is that this is tight, that once you reach maximum flow, that partition gives you the max cut, min cut, and this max flow algorithm also gives you this min cut for free. That is a nice thing about this max flow augmenting path algorithm, which when you stop, in fact, a way of proving that you have stopped and you have achieved the maximum is that you get a cut of minimum capacity. Okay. So, I am going to assume this theorem, you can check this out, and I am going to assume that there is an algorithm to find the max flow, which will also give you this min cut. Okay. So, I want to prove that if there is no flow, I mean the maximum flow is strictly less than G star, then the min cut is going to give me the set of the form I want. Okay. So, that is what is left to show. Okay. So, if max flow is less than G star, which is equal to summation G x y, let S bar be the min cut. Okay. So, it is a cut of this vertex set. The min cut may have some of these u x y vertices, some of the z vertices. So, it could be like this, right. Your min cut is just a partition of the vertex set. And I want to look at the capacity of this cut, which is sum of the edges, capacities of the edges going from S to S bar, and derive this. Okay. So, we will make some first observation, some simple observation. If u x y is in S if and only if x and y are in S. So, I have a min cut, this S and S bar, which partitions the vertex set. So, this S contains some u x y vertices, some v x vertices, and S, right. So, the vertices are of the two types. They are all like this kind of pairs, or okay, that is a claim. Okay. So, this cut capacity is of capacity, let us call this some f, which is less than G star. Okay. So, suppose u x y is in S, but x or y is here, what is the problem? So, one direction u x y is in S, but x or y is in S bar. Very good. So, you have, look at this capacity, I mean this is one of the things we did, this edge capacity is infinity, right. So, we said that capacity of this cut is some finite number less than G star. So, you cannot have this possibility. So, that shows that both x and y must be here if u x y is here. This is one direction. Conversely, suppose x and y are here, and if u x y is here, let us see what are the contribution of these vertices to the cut. Remember S is here and T is here, because that is the definition of ST cut. Okay. So, what is the contribution? There is nothing going from x or y to u x y in that direction. What about x and y will have some edges to T, yes, that is m minus w x, and this has an edge of g x y capacity going there. So, what if I just pull u x y and put it here? What do I get? A decrease by this g x y, right. So, that contradicts the fact that you started out with a min cut. So, I have a cut with smaller capacity. So, that shows that you can without loss and not without loss generally, if x and y are here, ux y can be pulled here. Okay. So, good. With that, now we will analyze the capacity of this cut. So, capacity of S bar. So, now how is S bar? So, there are some uxy's, let me just, yeah. So, if you have a uxy here, then there is a contribution of gxy, right. So, this is equal to summation gxy whenever uxy is in S bar plus uxy is in S means that x and y are here, and so the contribution will come from these edges. Okay, let me write it and then we can see, plus m minus wx plus m minus wy whenever uxy is in S. Is that clear? I have just split what is the, so if uxy is sitting here, then I know, I argue that x and y are here. So, there is a contribution of x to t, y to 2 edges. Remember, you have to look at this construction here, the edges are of very special form. In particular, there is no edge from uxy to t, there is no edge from S to these vertices and so on. Okay. So, if uxy is here, then if uxy is here, there is this edge contributing gxy. If uxy is here, x and y are here, so there are edges coming from this. Okay. Okay. So, this is, okay, let me write this as gxy, x or y is in S plus m into cardinality of S plus minus summation wx x in S. Okay, so now I have to make, sorry, one thing I have to make it clear. So, this S contains what nodes of the form x, y and uxy. So, I am going to let T equal to S intersection the teams. Okay, so let me make that different. So, in this S, I have vertices of the form that correspond to pairs of teams, and then there are vertices corresponding to teams. So, I will pick only that corresponding to the teams, that is going to be my final T here. I have to exhibit you a subset of teams, and that is going to be this teams. Okay. So, so, if uxy is here means that you cannot have both in S. So, one of them is not in S. Okay. So, I should write x or y is not in T. Yeah. Okay. So, that is what I have. So, let me complete it. So, this is equal to total games is G star minus summation gxy, xy is in T plus m times T minus summation wx, x is in T. And this whole thing we know is equal to f, which is less than G star. I make this simple observation, and from that it turns out you can compute the capacity of the cut. and the capacity of the cut is this. So, some gxy x or y is not in T, I have written it as g star minus gxy, where both x and y are in T, okay, and that is it, I am done. This whole thing is the capacity of the cut, which is f, which I know is less than g star. So, let me cancel this g star, and what I have is summation gxy xy in T plus summation wx x in T is strictly greater than m times T, and that is what we wanted to show. The T is the role in playing the role of the set time after. Okay. So, now you can write a program at any point of time. You know the games to be played, the points won so far. Think of a complex EPL where they play some 38, each team plays some 38 games. Now you can write a program, model it as a flow, run the max flow algorithm. Every feasible flow will give you a possible way of the outcome of the remaining games, so that your favorite team remains highest, possibly tied, or you will get a witness of this form which tells you that the team has been eliminated, okay. And you just appeal to this, it does not look like a graph problem or a flow problem, but it is, there may be many other ways of solving this, but I find this a nice elegant way of an algorithm as well as a witness for both. If it is not eliminated, here is a sequence of outcomes which will give you that this guy wins, and if it is eliminated, here is a justification why, because there is a subset which has this property. Okay, stop here. Thank you. Any questions?